And so I'm going to talk about why we actually need negative emissions and global pathways to net zero. And for that, I brought those pathways from the latest IPCC assessment. So early next year, we're expecting Working Group 3 to come out with the next assessment. So these pathways are from the 1.5 degree report. And what you see is that all of those pathways that reach 1.5 degrees ultimately at the end of the century share three distinct features. One is this immediate turnaround of emissions and then rapid and deep emissions reductions already before 2030, then reaching global CO2 neutrality in the middle of the century. And then afterwards, all of those pathways dive under the zero line, which means that we withdraw more CO2 than we're emitting back into the atmosphere. So we're net negative, so to say. And really, in this assessment, there was not a single pathway that could reach 1.5 degrees at the end of the century without withdrawing CO2 from the atmosphere. Even those that explicitly tried to do so without CCS, without bioenergy and CCS, they were still withdrawing something around the order of magnitude of 100 gigatons CO2 cumulatively until the end of the century, mostly then by afforestation, but that's something I'll get back to in a minute. First of all, let's look at what we're actually talking about when we talk about net removals from the atmosphere. First of all, please look at panel A, where we see what happens under climate change. We remove fossil fuels from geological formations, and then burning them adds CO2 to the atmosphere, and we're causing global warming. Now, if you substitute biomass for the fossil fuels, then yes, that biomass that's additionally grown sequesters CO2 via photosynthesis and thereby removes CO2 from the atmosphere. But then when you transform the biomass into bioenergy, you're releasing the CO2 back to the atmosphere. So at best, you're carbon neutral. Same is true for fossil CCS. So if you have carbon capture and storage on fossil point sources, then we're only removing what we previously got out of geological formations, and there's no net removal from the atmosphere. Only if you combine the two and don't let the CO2 that's sequestered in the biomass escape to the atmosphere again, but instead capture it and store it underground, you have a net removal from the atmosphere. There are other practices and technologies that remove CO2 on a net basis from the atmosphere. Direct air carbon capture and storage has been mentioned by Anna. Remove CO2 from the ambient air by means of a chemical reaction and then stores it underground. You can also enhance natural weathering processes by grinding certain minerals very finely, distributing them over larger areas, and then again via chemical reactions, the CO2 is bound permanently and removed from the atmosphere. And then there are a number of practices that have to do with enhancing our natural sinks. Most notably, I already mentioned it, planting additional trees that sequester CO2 via photosynthesis in additional trees. So in 2018, we conducted an assessment that also fed into the IPCC special report about what cost potentials and also side effects of the different options are in or would be in 2050. And of course, these are projections, so these are ranges. And you see that all of those technologies and practices I mentioned before have quite decent potential, something between 3 and 5 gigatons CO2, and these estimates are already conservative compared with other assessments. But there's still quite a broad cost spectrum. Direct air carbon capture and storage, for instance, is expected to come down substantially in cost, but is still at the upper end of the cost spectrum here. Things that we have more experience with, afforestation, soil carbon sequestration, they're at the lower end of the spectrum. However, you see them here with dashed lines, and that goes back to something that Anna mentioned already briefly. These are not permanent. So deforestation can go on, forests can burn down, and then the carbon that's previously been sequestered has to be considered as reversible. Same with soil carbon sequestration. If practices change, carbon can be released from soils as well. BECCS is here in the middle of the cost spectrum. And it has also been heavily criticized because if you look at the kind of removal scales that we've seen in the scenarios I've introduced in the beginning, then you sometimes see double-digit gigaton scale removals. And if you do all of that with BECCS, then of course you have to plant a lot of biomass. And the land that's needed for that might also be needed for other purposes, such as growing food for a increasing world population, such as safeguarding our terrestrial biodiversity and so on. The same could, of course, be said about large-scale monocultures in afforestation, but it's been a point that has been recurrently brought up in the context of BECCS, which is why I'm mentioning it here. All in all, I would say all of those come with their specific advantages and disadvantages, and what we'll probably be headed towards is really a portfolio of these things. And none of them really represents a silver bullet here, but what we have to really take back from this is that it's now time to step forth from the global pathways and really see what makes sense in which context. And that's why I brought here the case of Sweden, where you see for the case of industry, all the different point sources. On the left-hand side, the smaller ones, on the right-hand side, the bigger ones above 500 kilotons. And they are conveniently located along the coastline, which means that if they were retrofitted with CCS, the CO2 could also be transported quite conveniently. And then if you also look more closely into these, a lot of those point sources are actually already of biogenic nature. So that means you would get BECCS without sacrificing another hectare of land. And those have here been ordered in a kind of marginal abatement cost curve. These are the ones only from the right-hand map, the 27 large industrial point sources of CO2 emissions, and the green ones are those with biogenic CO2. That means quite a substantial portion would result into BECCS, and in the end, this would correspond to more than half of the total emissions from all sectors in Sweden. So I think that serves to illustrate that, yes, if you look at the global pathways, some of this might actually look quite scary, and you might get worried that you don't manage to do this with respecting other sustainability goals. But then if you look in specific context, there are, of course, risks, but also opportunities. And it's important to not lose sight of also other technologies and practices that could be used to fill this gap. Talking about the gap, if you look back, if you remember the different pathways I've shown you in the beginning, and then you look around, what you actually see in reality becomes quite clear that we're looking at a big innovation gap here as well. And a colleague of mine has actually made a very attractive back of the envelope calculation just to illustrate what we're talking about, taking a successful technology that scaled up quite rapidly, solar PV with the first commercial application in 57, and then reaching low cost in 2017, but still being a couple of years off from widespread adoption. If you would translate that one-to-one to direct air capture, which had its first commercial deployment in 2017, then we would see low cost installations in the 70s and widespread adoption at the end of the century, which is not what we really see in the pathways I've shown you in the beginning. So really what we need here is an acceleration of innovation. And today we're also, of course, discussing the instruments that would enable us to accelerate such an innovation. What I also want to match this gap that we see in reality with is the knowledge gap here. So we have really an increasing knowledge base on the different CDR options, the practices, the technologies. We know more now about removal potentials, costs, side effects, even systems integration. But then when we tagged all the literature that we looked through for their innovation stage, we saw that, yes, we do know a lot on the supply side. There's a lot of literature on research and development, but we know very little when it comes to the demand side, niche markets, demand pull, public acceptance, policy. But this is really the knowledge that we need when it comes then to putting this into national net zero legislation. So we need both, closing this knowledge gap, but also finding innovation models that are applicable to ramping CDR up in an unprecedented way compared to other technologies. What I didn't mention before when I discussed the different technologies and introduced them was what Anna briefly touched upon as well, CO2 utilization. It's a very attractive narrative, of course. We don't consider CO2 any longer as a waste, but we consider it as a resource. Circular economy is a term frequently floated here. It's, of course, a cheaper and cleaner feedstock. It could facilitate other CCS technologies. Lots to speak for it. But in a systematic review that we did with colleagues from University of Oxford, we found actually very little pathways that could, in the short term, really lead to net removals from the atmosphere. And on the contrary, if you look at what systems these take place in, you could even increase CO2 emissions. For instance, if you need a lot of non-decarbonized energy input to transform something into a synthetic fuel where the CO2 is released also shortly after again. So really what you need to look at is, where does the CO2 come from? Where does it eventually go? How long is it bound in the product? What kind of system are we looking at? Like, what's the carbon footprint of this transformation, and what does the product really substitute in order to come up with a final emissions balance? And that's what actually should feature in legislation and incentivization. So we found that it would not be useful to remunerate utilization per se, but really to look at the emissions balance and to remunerate what could be avoided in terms of CO2 emissions or even removed. Finally, let me close with a couple of thoughts on our today's topic, and these are really points that I think we can take into the discussion later on. In principle, if you look at it from an economic standpoint, then you would there's nothing that speaks against equal pricing for emissions, avoided emissions, and CDR. In reality, however, you have market failures, externalities, technology-specific distortions, so there could be a case for price differentiation. Concerning international emissions reductions, yes, there is a potential cost advantage from emissions transfers, buying CDR from somewhere else, but at the same time, an EU focus initially can make a lot of sense for different reasons. There'll be learning effects. We see a lot of pushing in this direction now in the US market, for instance. And also, if you look at negative side effects you want to manage, you can obtain better control there. When it comes to innovation acceleration, there are, of course, a lot of technology-specific instruments there. But if you look towards an EU market, a long-term announced minimum CO2 price for CDR could be an additional incentive, plus also a regular review process to bring on new technologies. This is really a dynamic process, and I think that's something that needs to be taken into account. All of this, of course, needs precise monitoring of removals, so we can actually verify how much was removed, for how long it was removed, so we can remunerate that and also measure really the climate impact. So this is really key and a key investment to make for all of this. So while in the shorter time you might want to target a specific CDR options individually, and here we're also looking at instruments like, for instance, Innovation Fund. Eventually, if you want to go towards a price-based approach, you will also need to take these technology specific aspects on board. So supplement this with additional regulations that can account for technological, ecological, and economic aspects. Finally, a very last point, because it's so prominent in the discussion, is the concern that you might have unwanted interaction with climate change mitigation. So the mere possibility of being able to clean something up later on, leading to less climate actions in the short term. But there are also a couple of proposals here how you could circumvent that. Countries are discussing to separate the targets for CDR and emissions reductions. Sweden, for instance, was discussing a reverse auctioning principle. Also, if you look at technologies like BACs and DUCs with a different cost structure, the Rickers et al. Paper was arguing even if you would integrate that into the EU ETS, that could actually that would actually not undermine other mitigation options. So just to give you a couple of points, couple of ideas, yes, this concern is something that's perceived, taken seriously, but there are also solutions around that are currently being discussed. So with that, I want to close and give it to the next speaker. Thanks for your attention.